Hey everyone, and welcome back to The Explainer. Today we're tackling a topic that sounds like a total mouthful: one-dimensional, continuous, random variables. But don't let the math jargon scare you. Honestly, it is just a really beautiful, visual way to model the messy, fluid, real world around us. It's like a giant puzzle, and we're going to take a super simple journey to put it all together. Let's dive in. Here is our quick roadmap for today. First, we'll define what continuous variables actually are. Then we'll draw out the probabilities, check out some really helpful computer programs, look at measuring the averages, and finally, wrap things up with some concluding thoughts. A clear, step-by-step path to demystify all of this.
Okay, let's dive into this. Section 1. What are continuous variables?
So by definition, a continuous random variable is a variable whose values can take any real number within a given interval. What does that actually mean in plain English? Well, practically speaking, it just means we are measuring things that don't land on clean, exact, whole numbers. They fall within a range. Think about the exact temperature outside, the precise time it takes you to run a mile, or even the exact weight of an apple. These measurements don't just hop neatly from 1 to 2 to 3. They flow continuously, and they can fall literally anywhere within a specific range. Now, the source gives us a few super simple ground rules for how these continuous variables behave. First off, their values belong to real numbers. So, decimals and fractions are completely normal here. Second, they use what's called a probability density function. It sounds fancy, but it's really just the mathematical model that creates that smooth, continuous curve on a graph. Third, we calculate probabilities over intervals. We're looking at the chance of a result falling between 2 points, not just hitting one single exact dot. And finally, we calculate cumulative probabilities, which simply means adding up the total probability across an entire range.
Let's transition from those abstract rules into visual reality. Section 2. Drawing the probabilities.
Now, what's really interesting about this is how probability in a continuous world becomes a physical area. Notice that shaded brown area in the middle graph? That colored-in space between point C and point D under the curve literally is our probability. Like we just talked about, we calculate over an interval. So the curve maps out our data, and that continuous volume of space between our two markers tells us the exact odds of our result landing in that specific range. It's kind of brilliant. It takes a complicated integral and turns it into a simple, colored-in visual area.
All right, Section 3. Helpful computer programs. Look, let's be real. We don't have to draw these complicated shapes or calculate messy integrals by hand. Thank goodness, right? We have specific software tools, like Graph and GeoGebra, that are built exactly for this. Those logos you see? They represent programs that make visualizing these continuous random variables a total breeze, doing the heavy lifting for us.
So the crucial point is that these programs do 3 very simple jobs for us. Number 1, construct the functions. You just plug in your parameters and boom, the software plots your probability density function. Number 2, visualize the areas under the curve. The program automatically calculates and shades in that exact interval between your chosen points. And number 3, calculate the probabilities. The software spits out the precise math derived from that shaded area. It's literally just build the function, visualize the interval, and let the program extract the probability.
Let's move to Section 4, Measuring the Averages, and see how this builds as we transition to the basic rules of calculating our findings.
Now, we don't need to get bogged down in the heavy calculus from the source right now. We really just care about what these functional outputs tell us about the center and the spread of our data. First up, we have the average, also called the expected value. It's represented by the Greek letter mu. Actually, scratch that. Just think of it as finding the true expected center of our distribution. Next is variance, which calculates how far our data spreads out from that center. Then, standard deviation takes that variance and puts it on a standardized scale, so it's much easier for us to grasp. And finally, the coefficient of variation. This compares the spread directly relative to our average. Basically, these measures give us the whole shebang, exactly where the middle of our continuous distribution is and exactly how far the edges stretch.
And we made it through the math. Section 5, Final Thoughts.
And this brilliantly illustrates the absolute perfect way to wrap up. The source material ends with this fantastic cat meme. For those who don't read Spanish, the text translates to, "Thank you very much, applause is accepted, no questions." I absolutely love that. It is a super fun, tension-relieving reward from the author after powering through a robust walkthrough of one-dimensional continuous random variables. So, to wrap up our explainer today, I want to leave you with a thought. How might you use these tools to measure continuous, everyday things in your own world?
Seriously, now that you know how our probability density function works and how to find the center and spread of a distribution, where could you apply this? Maybe mapping out the exact arrival times of your morning train over a month, or accurately modeling the continuous growth of plants in a garden? This isn't just dry theory, you know. It's a really powerful, practical lens for viewing the fluid reality of the real world. Thank you so much for hanging out with me today, and keep learning.